everybody. So a couple of announcements that I'll make at the end of class. There was a typo on the kinematics card that I gave you all. I hope you saw one of the announcements. I'm going to be having an activity after class during office hours. If you want to stay behind and get a little bit more practice with motion, you're welcome to stay behind. I'll explain more of that later on. And as far as your homework goes, I'm not quite done grading it, but I've seen a lot of good work from you guys in regards to your homework. The one thing I will say is that there's been, I would say, a noticeable use of AI. Again, I would encourage you not to use AI. I would encourage you all to give your best attempt, and if you do use AI, try and use it more as a study tool rather than give it your question and have it answer it, because sometimes it does get it wrong, and for some of you, it did get it wrong on your homework. So just a forewarning about AI usage. As far as class goes, we're going to continue our discussion of motion. We're going to continue our discussion of motion in regards to the characteristics of our motional quantities. Increase the lights in here, maybe. That's a little better. So we're going to talk about motion. I don't know why I put an S at the end of that. We're going to talk about motion, and we're going to first recap some of the ideas of motion that we've seen so far. When we talk about motion, we start off with asking the question of where an object is located. The physical quantity associated with the location of an object, what do we call that? Position, absolutely. Now, if an object stays at its position and does not move from that position, that's very boring. We often like to watch objects and pay attention to objects that are moving. So when something undergoes a change in position, what do we call that? Displacement, absolutely. All right, well, displacement's only part of the story. Sometimes we want to know how quickly a displacement happens. When we look at the rate at which displacement occurs, what are we looking at? What's the physical quantity? Velocity, absolutely. And sometimes objects have a change in velocity. Sometimes objects speed up, slow down. Sometimes they change direction. When we talk about a changing velocity, what is the physical quantity we want to look at? Acceleration, absolutely. These are our four quantities related to motion. Now, the list actually is more extensive than this. We could talk about a changing acceleration. Sometimes objects undergo a change in acceleration, in which case we call it a jerk. Sometimes something's jerk changes. We call that a snap. If something has a snap that changes, we call it a crackle. And if a crackle changes, what do we think it's called? Pop. Snap, crackle, pop. That's a real physical thing, something that we will ignore because we will focus mostly on constant acceleration, unchanging acceleration. And all of these occur over some time period. So we have our motional quantity of position, displacement, velocity, acceleration, all of which happens over some time period. When we talk about position, velocity, displacement, and acceleration, I will remind you that each of these are a vector quantity. And the fact that it's a vector quantity means two things. That it has some magnitude. Its magnitude for position, how far away from the origin are you? Magnitude of displacement, how far did you move? Magnitude of velocity, how fast are you going? What's your speed? Magnitude of acceleration, how quickly is your speed changing? That is the magnitude. They also have directions, right? Position could be, the stapler is about half a meter to the right of me. Or I could say this little informational pamphlet thing is half a meter to the left of me. Direction matters with position, with displacement, velocity. Saying you're going north is a lot different than saying you're moving south. So direction matters with all of our vector quantities. Time, however, time does not have direction. Time is a scalar quantity, meaning it only has a size. We cannot have a negative time. Negative time doesn't mean anything. You can't travel backwards in time. If you can, please share your secret with me. But as far as I know, time only moves in one direction, so there's no use in defining a direction for time. Time is a scalar quantity. We then move on to say, well, what kind of mathematics can we do with this? Well, we look at our definitions. We say an acceleration we can define an acceleration to be the rate of change of velocity, meaning how quickly is our velocity changing. We put a little arrow over v and a little arrow over a to indicate that these are vector quantities. They have directionality. And for the case of this class, we will usually take acceleration to be a constant. For the sake of this class, we will mostly say acceleration has some constant value. This is our definition of acceleration. Acceleration is dv dt, the rate of change of velocity. And we say, okay, well that opens up the questions, what is velocity? Velocity can be described as the rate of change of some position, dx dt. Or dy dt, or dz dt. Whatever positional quantity you want to look at. We're looking at horizontal motion, vertical motion, motion into and out of the board in that third dimension. However we want to describe it. This gives us our definition of velocity. Now last time we took this definition, we put the dt on the other side, we made an integral, and from that we found that velocity can be described by taking your initial velocity and adding to it your acceleration times time. Your acceleration, which is a constant value. Your acceleration, which is unchanging. Then we say, well, what about position? What about position? Well, we can say position is related to velocity, right? And we can take this definition of velocity, pull the dt to the other side, integrate across the velocity v naught at, and what you would find is that an object's position, we'll take horizontal motion to be our consideration here, so we'll use x, but we can swap out that x with a y or a z if we so chose. We say that our position is given by our initial position plus our initial velocity in the x direction. Specifically saying the horizontal component of our velocity. We looked at components of vectors a while back. This is the horizontal component of your velocity. Multiply this by time, and we add to it 1/2 acceleration times squared. Again, looking at acceleration specifically in the horizontal direction. And this is how we can find our position, given once again that we have some constant acceleration a. And perhaps I should be consistent here and put x's on my subscripts of all my velocities and accelerations. But we have this relationship for our quantity. You say, well, what about displacement? Displacement is simply the change in position, your delta x. Well, how do we find that? We take x naught, our initial position, subtract it over to the other side. What we have is v naught xt plus 1/2 acceleration times time squared. It's the same equation. The difference between displacement and position is just that displacement is your final position minus your initial position. We then ask the question, how do we put this into use? How do we put this into use? Well, we can consider the motion of a free-falling object. So we take all of this and we consider the motion of a free-falling object. So I'll use green here to represent my free-falling. Can we see green? Raise your hand if green is a little hard to read. All right, if we can see green, then I'm going to go ahead and use it. So free-falling motion. Well, what is free-falling motion? Free-falling motion is defined by an object that is in the air, and the only thing acting on it is gravity. Gravity is the only thing acting on an object. It doesn't necessarily mean that your object is moving vertically downwards. This includes objects that are thrown vertically up. Those of us in lab did an experiment today where we threw an object up. We saw free-falling motion where an object might be thrown vertically upwards by a person, and as soon as it leaves the hand, the moment that the object leaves the hand, it is considered in free-fall motion. How do we define free-fall motion? Well, it's defined with a very special acceleration. The acceleration of a free-falling object is given by negative 9.8 meters per second squared j hat. What does that j hat mean? Vertical, absolutely. J hat means vertical. What does the negative and j hat combined tell us? Not necessarily that it's acting against something, it's the direction. It's the absolute Cartesian direction, meaning that it's telling you it is vertically downwards. And it should make sense. Every time I've dropped an object, it's accelerated downward. So it should have a negative j hat associated with it. The negative j hat is the direction part of the vector of acceleration. The negative j hat is the direction. And the 9.8 is our magnitude. The 9.8 is the magnitude of our acceleration. And that's how we define our free-falling objects. Okay, we give it some other information. Perhaps we look at an object, we throw it into the air. I will define a problem for us. Perhaps I ask the question, if a rock is tossed vertically up at a speed of, don't want to use 10? Yeah, why not? 10 meters per second squared. That decimal point means that we have two significant figures. So I define a scenario. Physics is all about defining and analyzing scenarios. Here's the scenario. You toss a rock vertically upward at 10 meters per second squared. And then we ask something about this scenario. We define the scenario, then we ask a question about it. The question might be, how fast does it move after 1.5 seconds? How fast does it move after 1.5 seconds? So we define a scenario, we throw a rock upwards at 10 meters per second squared. We ask something about the scenario, making a prediction. What is its speed after 1.5 seconds? We look at this and we say, well, I know its initial velocity. Its initial velocity is what? 10 meters per second, not squared. Acceleration is squared. Oh, I shouldn't have put that squared there. Sorry. My bad. But the velocity is 10 meters per second. But velocity needs direction. 10 meters per second. Short, up, positive. Positive what? Positive j hat. We would say V naught is given by 10 meters per second positive j hat. That is the vector quantity of velocity. We then ask, okay, well, what is the acceleration? What is the acceleration of our rock after we toss it vertically upwards? Negative 9.8 meters per second squared. J hat, absolutely. That j hat is important. That j hat gives us direction. So we have our acceleration, 9.8 meters per second squared, in the negative j hat direction. And it will always be this. This is a constant value. This acceleration does not change. We go on to ask, what is the time? What is the time that we are looking at here? How long into the future are we predicting? 1.5 seconds, absolutely. So we plug in the values, we can predict the final velocity. Wonderful. Perfect. We move on. We ask, Maybe we ask a second question. We might ask, what is the displacement? After 1.5 seconds. How do we find that? Once again, we approach it with our kinematic equation. We say our initial position. Well, we're always free to define our initial position to be the origin, the starting point, the point where we say the position is 0. So we might define for ourselves that x naught is 0. V naught x, well, we have that. This would be V naught y. But your initial velocity, we have 10 meters per second. J hat. Time, 1.5 seconds. Acceleration, 9.8 meters per second squared in the negative j hat direction. We have all the quantities. We plug it in. We use these equations to make our predictions. And this is where we sort of ended off last time. We defined these different motional quantities. And we looked at them specifically for these Cartesian coordinates. And in our Cartesian coordinate systems, we can use these same equations multiple ways. We can say that, yes, it works for x, but it also works for y, v naught y, plus acceleration in the y direction t. And y equals y naught, plus v naught y, t, plus 1/2 acceleration in the y direction t squared. These equations work for vertical and horizontal. They work in any of our well-defined Cartesian coordinate systems. But we don't always want to strictly use Cartesian coordinates. Some motion is too complicated to really discuss in Cartesian coordinate systems. So let's discuss what happens when our motion is not well-defined in our Cartesian coordinate system. I will set up a Cartesian coordinate system here. That is just to say we have an x and a y, a vertical and a horizontal piece, and we are going to look at motion of a rotating object. To demonstrate this, I brought a wheel. What we're going to do is we'll focus on this yellow sticky note right here, or this yellow, I think this is a piece of tape. This yellow piece of tape, right? We're going to look at it and we're going to see, well, it goes up and then down and then up. We track it over time. We say it starts off. We say the yellow sticky note starts off perhaps right here. It proceeds to rotate vertically upwards. So at some point it'll reach that location right there. I'm trying to write with my left hand. And then that yellow piece of tape will continue to move. Eventually it goes to the negative x-axis, and then it continues to rotate. Eventually it goes downwards, right around there. And then it returns back to our initial position. What does that look like on our Cartesian coordinate system? Well, we start here. We might call this our position initial. And as we go through time, we have a rotating object following that line. Now, that's complicated to look at, right? That's complicated because we have both x and y changing at the same time. Now, those of us who have taken trig and are familiar are like, well, just use a sine and cosine. I don't want to use sine and cosine. Sine and cosine is hard. So we'll do something different. Instead of looking at the x and y changing at the same time, we'll define perhaps our positions a little bit differently. How do we do that? Well, we take a look at this yellow mark. We'll take a look at this yellow marker right here. We can say it's maybe about 12 or 15 centimeters from the axle, right? We go up. That distance does not change. It does not get any further away from the axle as it goes throughout its spinning, right? But what can we say does change? the position changes, the distance from the axle doesn't. Well, what might change? We might say we are rotating through some angles, right? We can say that we start off to the left. We can say we rotate 90 degrees to be vertical, rotate 180 degrees to be flipped totally around, 270 degrees, and then 360 degrees for our rotation. Do we see that? As we go through our rotation, we are changing the angle that we are looking at. Where we define perhaps the position that we start off at to be a position of 0 degrees. And we rotate upwards. Perhaps when we're right here, we say, well, that's about 45 degrees. When we're up here, that's about 90 degrees. And then we keep on going, and we can define all of these different degrees, right? 180 degrees, 270 degrees. And you can define any position on here with an angle. So now we can define the position as saying it is some distance away from the axle. We say it's 15 centimeters away from the axle, and we define an angle to specify where it is located. So we define the position with relation to the axle as being some distance and an angle. And that gives you a non-arbitrary location where the position of this object must be. Because if I say the position of that sticky note is 15 centimeters, we'll say this is 5 centimeters, 10 centimeters, 15 centimeters. If I say that the position of the axle is 15, or the position of the sticky note is 15 centimeters from the axle at 0 degrees, that must mean its location is right there. It can't mean anything else. If I say it's 45 degrees, it's at that 45 degree place. It can't be anywhere else. So we now define a position not by an x coordinate and a y coordinate. Rather, we define a position based on the angle that it's at. Typically in physics and mathematics, we represent theta for our angle. For our angle. So we now say a position is given by some angle theta. And that theta is changing over time. We have a theta that is changing over time. Well, if our theta is changing over time, what can we do? We can say that there is some velocity that represents this changing theta. And we use the Greek symbol omega to represent our angular velocity. Bless you. This is just looking at how quickly your angle changes. If you ever look at your car, it'll tell you how quickly your engine is rotating every minute, RPM, right? That RPM is an angular velocity. It is telling you how much the angle, or in that case, how many revolutions are happening in a given time period. Theta was our angular position. Well, when we look at an object, it can certainly have a changing velocity. We look at this wheel, for example. If I give this wheel a spin, it has some angular velocity, and over time it slows down to having no angular velocity. That means the angular velocity must have changed during that time. We could talk about a change in velocity. Well, before we called that an acceleration. Here, we might call that an angular acceleration, represented by Greek letter alpha. Alpha is our angular acceleration, which describes a change in angular velocity. So what do we do here? We create a new coordinate system. We create a new coordinate system where now instead of describing x and y as our positions, we say theta is our position, whatever angle it's at. That is our position. We say instead of a velocity v, we are change in angular position. Well, that's going to be omega, our angular velocity. And if that angular velocity changes, we define an angular acceleration, alpha. Now I put arrows over them. What does an arrow over a quantity mean? It's a vector. So this angular velocity, for example, it must have two things. What two things must it have? Direction and magnitude. Absolutely. And when we look at this, we say, well, what do those quantities mean exactly? Well, for our spinning wheel, we can define the magnitude by how quickly it's spinning, right? We say, well, that's spinning kind of slow. That is a small angular velocity. We spin it more quickly. Larger angular velocity, larger magnitude, right? The magnitude is just how fast is it spinning. But what might direction mean? What do we think direction means in this context? Whether it's clockwise or counterclockwise. We have motion that is that clockwise for you guys? Yeah. We have motion that is clockwise. We have motion that is counterclockwise. That is the difference in direction. And before we define our direction to have some positive or negative value associated with it, right? We said that upwards is positive and downwards is negative. Right is positive, left is negative. Here we want to assign a positive and a negative for our angular motion. So we look to mathematics to understand, well, which do we want to be positive or negative? And the determination that we use is we say that counterclockwise is the positive rotational quantity. So when you have omega being a positive value, that means it's moving counterclockwise. When it's negative, that means it is moving clockwise. So we might say that our angular velocity omega, when omega is greater than 0, when it is positive, that indicates counterclockwise motion, CCW, counterclockwise. So we have our motion defined with a directionality. Does that sound good so far? Question?
You said magnitude can change with the wheel?
Sure, the magnitude of the velocity can change. When we look at this, it is spinning. Is it spinning clockwise or counterclockwise? So is it positive or negative? Okay. Now, is it staying the same speed or is it slowing down? It's slowing down. Its magnitude of its velocity is changing. It's going from having some positive velocity to 0 velocity. Its velocity changed. Just like an object can speed up or slow down, it can spin faster, it can spin slower. And whenever we have that changing angular velocity, that's when we have our angular acceleration. Sound good? Now we are going to look at the cases, strictly speaking, with angular acceleration being constant. Why do we do that? We do that because it simplifies the mathematics significantly. It ends up being a good representation for most motion, having a constant angular acceleration. So we say angular acceleration is a constant. And more to the fact, we say angular acceleration is defined to be the change in angular velocity with time. That is our definition for angular acceleration. The change in angular velocity over time. Just like acceleration is a change in velocity. Well, now hold on. This looks familiar. That looks familiar, does it not? Where have we seen something that looks like this? With acceleration velocity, traditional acceleration, traditional velocity. So, if that is the case, mathematically, we went from acceleration dv dt, and that gave us this relationship for velocity. Mathematically, our two definitions are equivalent. We swap out the a for an alpha, we swap out the v for omega, and what comes of that? Well, we should end up with something of the same form. So we say this is going to give us omega is equal to our initial angular velocity plus our angular acceleration times time plus alpha t. We end up with an equation of the same form because the mathematics is identical. We still have just a changing coordinate, a changing angle in space. And we still have a defined constant acceleration that is defined as the change in velocity over time. So we get the same omega is omega naught plus alpha t. Mathematics is identical, so we end up with the same result. We go on and we say, well, what is omega? Omega, our angular velocity, is defined to be the change in position with respect to time, how quickly our angle changes over time, d theta dt. And we look at this and we say, well, this is also familiar. A velocity is the derivative of position with respect to time. Velocity is derivative of position with respect to time. Again, we've seen this. And since we've seen this, the mathematics that takes us from point A to point B, our definition of velocity to a way to describe position, the mathematics is the same. It's identical. So what does that mean? That means that this definition gives you theta, your final position of your object, is equal to your initial position, theta naught, plus omega naught t, right? Position is initial position plus velocity times time. Position is position initially plus velocity times time. Just swapping out our traditional Cartesian coordinates for our angular coordinates. And then we add to that what? 1/2 our acceleration times time squared. 1/2 our angular acceleration times time squared. And these are all vectors. So you can include our vector arrows. And we end up with an equation that is identical. Identical to what we've had before. And we can describe a change in angle, delta theta, angular displacement. An angular displacement that's omega naught t plus 1/2 alpha t squared. We just take delta theta to be our final angular position, our final theta, subtracting off our initial theta. So we take a look at this. And once we do all of this, we can start to see that our constant acceleration equations, v equals v naught plus at, we'll use x as our example, x naught plus v naught t plus 1/2 at squared. They're the exact same equations for our angular acceleration being constant, such that omega equals omega naught plus alpha t, and theta equals theta naught plus omega naught t plus 1/2 acceleration times squared. And I should put alpha there. We get the same equations. All right, well, we test this. We say, well, what do we think? The kinematic equation would come out to in our angular case. What do we think this will come out to? I want you to take a second and to jot down what the angular equivalent to this equation should be in your notes. Take a second, jot down what do you think the angular equivalent to that third equation should be in your notes. All right, who wants to venture a guess? What is the angular equivalent to that third equation? What do we think?
Omega squared equals omega naught squared plus 2 alpha theta.
Absolutely. We just swap out the terms. And you'll see as we return to this angular motion stuff over and over again this semester, every time we return, it'll be the same story. That we just take our linear motion equations, our Cartesian coordinate equations, and we just swap out our angular terms. Why does this work? Well, this works because our angular coordinate system is just as good as any other coordinate system. So the mathematics follow through to just let us replace them. All right. Now, we ask the question, how does this apply to the real world? How does this work for us? How does this help us? We might ask the question, a record spins from rest to 45 revolutions a minute. What does this mean? This means that a record, I've got a record player, a record will spin around in a circle 45 circles in 1 minute. So you time it out for a minute, it will spin around 45 times. We're going to say that it spins up from rest to this speed in 3.3 seconds. I can ask two things here. Because we are given our initial and our final velocity, we are given our time. I can ask two things here. I can ask a question of what will the angular acceleration be? If I could spell today. Angular acceleration. I can ask, what is the angular acceleration during this time? I set up a scenario. I set up a scenario that says a record spins from 0 to 45 RPM in 3.3 seconds. Then I ask a question, a prediction question. What is the angular acceleration? Well, how do we solve this? We pick out one of our kinematic equations. Perhaps omega is omega naught plus alpha t. Our initial angular velocity plus our angular acceleration times time gives us our final angular velocity. So we pick out the equation that matches our scenario. Rotational problem needs one of these rotational equations. From here, we ask the question, what is the angular acceleration? We just algebraically solved this for the acceleration is equal to our final angular velocity minus our initial angular velocity divided by time. We just do the algebra. Not too bad, yes? And then we ask, well, what is our initial angular velocity? What's our initial angular velocity in this problem? 0. How do we know? We know because spins from rest. Rest means stationary. So your initial velocity is 0. Your final angular velocity, what's your final angular velocity? 45 revolutions per minute. And then the time is what? 3.3 seconds. So we take 45, we divide by 3.3, and I say that's wrong. Why is it wrong? Because the units, one is minutes, one is seconds. So here's what we're going to do. We are going to do the unit conversion before we do our mathematics, and we need to make a decision. What do our final units want to be here? Do we want minutes or do we want seconds? What is our choice? Seconds, minutes. I don't specify here. You could choose either. Now the base SI units, the base SI unit would be seconds. So perhaps we want to do revolutions per second. So we say 45 revolutions per minute. We multiply it by the unit conversion factor from minutes to seconds. We say 1 minute is how many seconds? 1 minute is 60 seconds. Absolutely, that'll cancel out our minutes. And then we divide that by 3.3 seconds. So you do 45, divide that by 60. Get a number a little bit less than 1. 45 divided by 60 is what? Point what? 0.75, thank you. So we have 0.75 revolutions per second. Divide that by 3.3 seconds. Someone shouted out the answer earlier. What was the answer? 0.23. Is that right? Looks about right to me. Revolutions per second squared. That's our angular acceleration. Wonderful. We did it. We solved for our angular acceleration. This is the same exact problem as any Cartesian coordinate problem, where I give you some initial velocity and some final velocity and some time. Same exact problem. So then the question might be changed. We might ask a different prediction question. We might say, what is the displacement during this time? And this is the same exact type of problem we asked last time. When I said, what is the displacement, your change in x? Given a velocity, a time, and an acceleration. We do have the acceleration now, 0.23 revolution per second squared. So at this point, we can look for our displacement. The only difference now is it's an angular coordinate. So our displacement, delta theta, is given by initial angular velocity. What is our initial angular velocity here? 0. Multiply 0 by time, we still get 0. Plus 1/2 your acceleration 0.23 revolutions per second squared. And then time squared is 3.3 squared. So we can do this to find the displacement. Go ahead, find the displacement, show it to your neighbor, make sure you and your neighbor get the same exact displacement, and make sure we can solve for this type of problem. All right, how many of us were able to find the displacements? Who has a question before I seek out answers? Any questions out there? Any thoughts and comments? All right. So, how did we find it? How did we find this displacement? What was the process?
State your knowns.
Sure, we state our knowns. What are our known values? What do we know?
0 for angular velocity.
Okay. 0 for our initial angular velocity. Someone else, give me another known.
Time is 3.3.
Time is 3.3 seconds, absolutely. All right, someone else, give me another unknown, or another known value.
0.23 revolutions per second.
Our acceleration, 0.23 revolutions per second squared. Thank you. What other unknowns, or what other, knowns do we have? Oh yeah, you can say your theta naught is 0, sure. Say your theta naught is 0 and your omega naught is 0 as well. We also have our final angular velocity. Our final angular velocity. What is our final angular velocity? 45 revolutions per minute. Thank you. 45 revolutions per minute. Or if we wanted to, 0.75 revolutions per second. All right, so from here, what do we do? From here, what we can do is break out our kinematic equation card. Look at our little kinematic equation card and see what falls into a useful category of equation here. There are quite a few that we can use. You can use that your displacement is equal to 1/2 your initial velocity, subtracting off your final velocity, multiplied by time. You have your kinematic card. That is the left-hand side, 2 equations down, just swapping out our omega and our v. That's one way we can do it. Well, what else can we use? Perhaps we say omega final squared is your initial omega, and I'm just going to keep omega final as omega, squared plus 2 alpha delta theta. Another equation that is usable. There's several on here. Multiple paths to a solution. No matter which path you take, though, you should end up with the same displacement. Delta theta, what is your displacement that you get for this problem? How many revolutions do we undergo? 3.3?
No, 1.3.
1.3 revolutions? Is that what we got? Raise your hand if you got something other than 1.3 revolutions per minute. Or sorry, 1.3 revolutions. All right, so we all end up with 1.3 revolutions. That means it undergoes 1 1/3-ish revolutions getting up to speed. Does that seem all right? Not so bad? All right, new question. New question. Child on a merry-go-round completes 2 revolutions while accelerating from rest to 5 revolutions per minute. It is not stated, but the angular acceleration is constant. Constant angular acceleration. I'm not going to give you problems with non-constant angular acceleration. So our angular acceleration is constant in this problem. And my question becomes, how much time passes during this acceleration? Again, we take the same path as we did last time. We list out our knowns. That's a great first step that Brian said. List out your knowns and your unknowns. What are our knowns here? Our knowns here. We read through the problem. Child on a merry-go-round completes 2 revolutions. delta theta is 2 revolutions. Okay, child on a merry-go-round completes a displacement while accelerating from rest. What does from rest tell us? 0 what? Angular velocity is 0 when? Initially. The initial angular velocity is 0 absolutely. Omega naught is 0. All right? Well, we go on. We read it. While accelerating from rest to 5 revolutions per minute. 5 revolutions per minute. What does that tell us? Final velocity is 5 revolutions per minute. And that completes our known values. Our known values. That's all. We ask, well, what are our unknown values? The unknown values we might want to list out. Time. That's a special one. That's a special one because that's what we're actually asked for. But we also don't know our angular acceleration. Another unknown. We know it's constant. We know it has some certain value, but we don't know what that value is. We can calculate it, but we don't know what it is. So we list out our knowns, we list out our unknowns. We consult the applicable equations. What are the applicable equations? Well, those are right here on your kinematics cards. We look at them and we say, well, the first equation on the left-hand side, that uses acceleration and time, not super useful to us. We look at the second equation, x is equal to x initial plus v initial t plus half at squared. That's an equation that, again, needs some correction, and we'll do that in a minute, but it's not applicable here. We don't know the acceleration, we don't know time. Too many unknowns. On the right-hand side, we have initial velocity, final velocity, acceleration, and displacement all represented on that first equation on the right-hand side. And we know the initial velocity, we know the final velocity, and we know our change in theta, we know our displacement. So we can use that first equation on the right-hand side of that card. Ends up just being this equation that we wrote on the board. We can use that to find acceleration. So we could absolutely find acceleration if we wanted to. That's not what we're asked for, though. So we look one below that. And we get to the equation that delta theta is equal to 1/2 omega initial plus omega final times time. Did I get that right? Yes, I did. We look at that and we say, well, that has delta theta, we know that. We know our initial and our final angular velocity. And I guess I was using not here. Not initial, doesn't matter which you prefer. But we know both of those values, so we can just solve this for time, yes? And we go ahead and we look at this and just algebraically solve it, figure out how much time passes. We don't have to solve for acceleration. We can, but we don't have to, yes?
So if we solve for acceleration, can we then plug in what we got into an equation that has acceleration to figure out the time?
Absolutely. Absolutely you can. Absolutely you can find acceleration first. And once you have acceleration, find out that time. That's kind of what we did last time. We found acceleration, and once we had acceleration, we found some other value. You can absolutely find acceleration and get to the same time. All of these kinematic equations will lead you to the same result. All of these equations will lead you to the same result. And in fact, these other equations, if you look at the equation sheet, you have 2 on the right-hand column, 3 on the left-hand column. I arranged them that way in a very specific reason. The two on the left, the 2 equations on the left of your note card, those are derived equations. Those come from first principles, those come from accelerations. The 3 on the other side are just algebraic manipulations of the 2 on the left. So absolutely you can just solve for acceleration first and then plug that in. Okay, are there any questions? I'm going to have you guys solve this in a moment, but while I have everyone's attention, I want you guys to go to that kinematics card. And on that kinematics card, it is written on that kinematics card, there's an equation that's written as x final is equal to x initial times time plus initial velocity times time plus 1/2 acceleration times time squared. Again, I've mentioned it a couple of times, this equation needs to be fixed. So here's what I want us all to do. We are going to scratch out this equation. Scratch it out so that we know not to use it because it is wrong. And instead we are going to write in the correct equation. The correct equation is x final is equal to x initial plus v initial x times time plus 1/2 ax time squared. That is the correct equation. That first instance of time should not be there. So scratch out the incorrect equation, write out the correct one, somewhere on that note card. This is one of the few alterations I'll allow you to make. Okay. So, we're going to solve this problem. But before we do that, before I let you guys off to solve these problems, I want to make a quick note about what we're going to do next time. So, we spent this class. What did we do this class? This class, we went over this idea of motion. We said motion is described by position, displacement, velocity, acceleration, and time. And that's true of motion in any coordinate system. Doesn't matter if you use x and y or some rotational coordinate system. So what we've done is we've taken our work. We've taken our work from defining these accelerations and these constant acceleration equations. We've taken the work that we've done previously to derive these constant acceleration equations. And what did we do? We applied them to an angular case, where we now have an angular position, an angular velocity, an angular acceleration. So we take our equations and we turn them into something that's useful for our angular case. And then once we have that angular case, we can then solve problems that involve rotating objects. And as it turns out, the mathematics is equivalent to what we've done previously. Next time we are here, we are going to learn how to bridge the gap between our Cartesian coordinates and our angular coordinates. We're going to learn how to bridge that gap. In other words, how do we go from a velocity v to an angular velocity omega? That's what we will do next time. With the last few minutes that we have here, we are going to solve this question, figure out how much time passes before we reach our maximum velocity. While you guys solve that, I'm going to pass out a note card for this angular motion stuff that includes several of the equations that we will be looking at next time. And after that, I want to describe to you what's going to happen during office hours today, and I encourage you guys to stay for office hours. But for the meantime, solve that equation, figure out how much time passes for the child on the merry-go-round. Okay, everyone should have gotten one of these new note sheets, yes? Did I miss anyone? Okay, now share your time that you got with your neighbor if you did not already do so. Check that you got the same number as your neighbor, your closest friend in this class. All right, who wants to share the time that they got? What is that? 48 seconds? Seconds. Anybody get something other than 48 seconds? 9.6 seconds. Got perhaps a different time, 9.6. Any other times? Someone get something other than these two values?
0.8 minutes.
0.8 seconds?
Or minutes.
Oh, 0.8 minutes? 0.8 minutes, is that aligned with one of these two times?
Yes.
48 seconds. So we do have a discrepancy here though. So let's go ahead, let's solve this through as a class. We say time is equal to 2 times the angular displacement. Time is equal to 2 times our angular displacement of 2 revolutions. We take that and we divide it by omega naught plus omega final. What is our initial velocity? 0. So our final is going to be 5 revolutions per minute. 4 over 5 is 0.8 minutes, or how many seconds? 48 seconds. Sounds good to me. So that is our time. That is how we solve for our kinematic variables. We have time. Why not? Why not keep you guys here a little bit longer? Let's ask a different prediction question. Let's ask a different prediction question. Namely, okay, make this problem harder. Make this problem harder. Question is, if it were to accelerate at the same rate for half a minute longer, I forgot my R on longer. If it were to accelerate for half a minute longer at the same rate, how fast would it be going? How do you solve this problem? Well, to solve this problem, your first step would be to find the angular acceleration. Figure out what that value is. So you find that angular acceleration. Once you have that angular acceleration, you ask, well, how fast would it be going if it accelerated for now? How fast would it be going if it accelerated for 1.3 minutes? Because the original time was 0.8 minutes. we do a half minute longer, it is going to be 1.3 minutes. Apply that same angular acceleration for 1.3 minutes to find omega. This is a two-step problem. First find the rates, then extrapolate to find the final angular velocity. Go ahead, try and solve this one. And I encourage you to work with your neighbor. To work with your neighbor, check out if you can find the answer. All right, so for our last couple of minutes, let's focus up on the board. Quick show of hands, how many of us were able to get a final value? Don't share it, just raise your hand if you got a final value. All right, so let's go through a path to the solution. Now there are multiple ways you can get to the solution, including using that 0.8 minutes we found earlier. But I'm going to work off the assumption that this is the problem that was given as written. So if it's given as written, we have these as our initial known values. From here we can figure out that acceleration, the rate of change of velocity. And we find that by utilizing our initially known values. Our initially known values that our final omega is 2 revolutions per minute. No, wait, that wasn't our final. 5 revolutions per minute, like that. So we have 5 revolutions per minute squared minus 0 squared. I'll include the 0 there starting from rest. And then we divide that by 2 times delta theta. Delta theta here is 2 revolutions. So what does this end up being? 25 divided by 4 revolutions per minute squared. So this gives you the rate of acceleration. Do we feel all right about this?
6.25.
What is it?
6.25.
Yeah, sounds about right.
That's the same one.
6.25 revolutions per minute squared.
So they feel so.
It would be the same exact value had you solved it the first time we were doing this problem. Same exact value. We haven't changed any of our initial conditions. Now what do? Now we extend the time. Now we say the time is going to be a little bit longer. It's going to be 1.3 minutes. So we say, what is our final velocity? Our final velocity is going to be our initial velocity plus our acceleration, 6.25 revolutions per minute squared, multiplying that by the time of 1.3 minutes. So we extrapolate out to a future time, and when we do this, we should end up with 6.25 times 1.3. What does that give you? Say it loud. 8.125. 8.125 revolutions per minute, but wait. Significant figures. I only gave you one to begin with, so about 8 revolutions per minute. 8 revolutions per minute. This was a 2-step problem. First to find the rate of acceleration, then to extrapolate out some final velocity. All right. Now, quick note about office hours. I'm going to conduct office hours in this room because this room is empty after this class. If you wish to stay behind, you can do one of a number of things. You can work on your homework assignments that I've given you. You can work on the lab if you guys have had it on Monday. You can finish off some of those questions if you'd like to. You just stick back and hang out in a nice air-conditioned room. It's kind of a hot day. Or alternatively, I have a worksheet here on one-dimensional motion that I can give you that is a group work problem. But this is a worksheet that I've used in the past and helps students that are really struggling to visualize motion as it relates to one dimension. So I suggest staying behind and working on this if you have nothing else to do. It's good practice and it will help you when it comes to the assessment. What you do, though, is up to you. Covered that. I think that's all the announcements I need to make. So if you have any questions, stick back. Otherwise, I will see you guys on Wednesday.